Hi everybody, welcome to the short video where we will talk about Pitot Tubes and Venturi Meters, and the easiest way I can think of to explain it is by using the conservation of energy explanation. So here's a little bit of a diagram showing the basic principle of a large pipe narrowing to a smaller pipe, so we can use this to discuss the Bernoulli Theorem, which states that for an ideal fluid, the total energy of the fluid is constant for laminar flow. That means non-turbulent smooth flow. So we look at an ideal fluid in a pipe that narrows from a cross-sectional area A1 to cross-sectional area A2. We look at pressure in the large pipe as P1, velocity of the fluid as V1, and P2, V2 for the smaller pipe. We know that distance traveled, if we take this as a disk of fluid moving down the pipe, distance is velocity times time, and that's that V1t expression there and there. So we know from high school physics that work done by pressure on fluid is the same as the kinetic energy gained by the fluid, or PE equals KE. It's the basic conservation of energy formula. It's for all ideal systems. We say that we know that work is force times distance moved, or FD, and we know that force is mass times acceleration, so work is mad. It's a good way to remember this for me. And we know the acceleration is velocity divided by time, so we replace the a with v over t, and we established previously that distance is velocity times time, and you multiply that all out and you get that work equals mv squared. But work is also the derivative of energy with respect to velocity, which is equal to mv. So if we want to find out what energy is, E, we have to take the integral of this side of the equation. But if we take the integral of that side of the equation, we have to do the same on the other side. We multiply by dv to get the expression on that side. And if we integrate this, we end up with a general expression that E equals half mv squared. Now, when we're integrating, we want to know limits, and we're integrating with respect to v, so we put our limits as velocity 2 and velocity 1. And going through this equation again, inserting the v2, v1 limits, we get that energy is half mv2 squared minus half mv1 squared. Now, we have to look at mass here for a second, and we know that mass is density of the fluid times the volume. And the volume, if we look at the position of disk 1, disk 2, as it moves that distance v1t, it kind of traces out the shape of a cylinder. And so we have the volume being area times the height, or d. It's a typical volume calculation for a cylinder. And in this case, we know that d is vt. So we say that d1 equals v1t and d2 equals v2t, which we established earlier as well. And we replace the d expression with vt to make mass equal to rho density times area times velocity times time. And if we plug these expressions back into the integral we solved to get energy, we find that energy is half rho times the area of the larger cylinder times the velocity of the fluid in the large cylinder times t times the square of that velocity minus the same values for the narrower cylinder. We also know that pressure is force divided by area, so force equals pressure times area, and energy is force times distance, which if we replace the force value with PA, we'll get that energy equals PA, and D replaced with VT, so we get energy equals PA VT. So the change of energy is going to be E1 minus E2, and that will be the pressure 1 times area 1 times velocity 1 times time, less those values in section 2. And this is crossed out prematurely, but basically if we take that previous pressure version of E that we calculated, we can make it equal to the energy version of E, the kinetic energy version of E as we calculated previously, two sides of the equation. And we've said it's an ideal fluid with constant flow, so we have Q1 equals 2 Q2. Q equals the area times the velocity, is your flow rate. And so we have that the area 1 times the velocity of fluid in area 1 is equal to velocity of the fluid in pipe 2 times the area of pipe 2. And what we'll see is that if we say A1 V1 equals A2 V2, we can cross out these expressions as I've done here because they cancel, and the time expressions also cancel. So what we're left with is P1 minus P2 equals half rho V2 squared minus half rho V1 squared. And this is the full equation I'm showing here. This is the Bernoulli full equation derived. That's the pressure, energy per unit volume. This is rho GH, density times gravitational constant times height. We really only look at this expression if there's a vertical component to the flow, which there isn't in these examples, so that's 0. And the kinetic energy per unit volume. And this is obviously it's the potential energy per unit volume version. So we look at, now that we've done the Bernoulli equation, we can look at the operation of Pitot tubes. Now, if anybody's gotten onto an airplane, you've seen these strange L-shaped rods sticking out of various parts of the plane. These are the Pitot tubes, and these are the speed sensors of the plane. This picture is taken from isa.org, it's not mine. But basic construction of the Pitot tubes is it's one tube within the other. So if you imagine the yellow is an outer tube, and the white area is the inner tube. And the white tube is open directly to the velocity of the air. So this would be, the arrows are the direction of air as it enters the tube, and the tube is open to the front end of the plane, or the direction of flight. And these holes are tangential to the airflow. What that means is you can get all this air rushing in here, building up a PT, total pressure. And these tangential holes will only pick up the atmospheric or static pressure. And what you normally have here is you have a pressure transducer, which is some kind of electromechanical piezoelectrical material that will deflect based on the variations in this pressure and give an electrical signal which the pilot will then read via his dials. So if we use the equation we had before, we're assuming a plane is not changing altitude. That's a different meter that we're looking at there. It's an altimeter. We're not talking about that here. We'll say that P1 plus rho GH, but we're not changing altitude. We're constant height. Make that 0 plus half rho V squared. On the left-hand side of the equation, equal to that on the right-hand side of the equation. And where we'll say P1 is PT, the total pressure, and PS is the static pressure, and that'll be the velocity T and the velocity S. But because it's static and it's tangential, the velocity of the air in here is actually, you can take it as 0. The only velocity we have is the air flowing into the total pressure compartment. So if we make Vs equals 0, we'll get that Pt plus rho Vt squared is equal to the static pressure. And that's another way of putting it. And if you solve for V, you'll get, that's your answer. So, and some OEMs or manufacturers, there will be a constant scalar value, which you have to insert here. This you'll have to get from the manufacturer. But basically, that's the formula for how a Pitot tube converts pressure into velocity. So let's look at an example. This is from the Institute of Fire Engineers exam, March 2016, level 4, unit 1. First question is, using the energy equation and an annotated diagram, explain the operating principle of a Pitot tube. Well, we've done that. And the next question is, a Pitot tube fitted to the nose of an aircraft flying at altitude of 4,000 meters indicates a static pressure of 6.6 by 10 to the 4 pascals, or 66 kilopascals. Calculate the velocity of the aircraft. Take the density of air at 4,000 meters to be 0.8 kilograms per cubic meter, and the pressure of the air at 4,000 meters is 6.2 times 10 to the 4 pascals, or 62 kilopascals. So we just use that equation we had previously. Your static pressure, I told you, 6.6. Your air pressure, which is basically what's flying into the Pitot tube, or what the pressure it feels at 6.2, and divide that, you say 2 times the difference between divided by the density and take the root, and you come out the velocity of the aircraft is 100 meters per second. This is another IFE question taken from 2013. It says, using Bernoulli's equation, calculate the velocity in a pipe using a Pitot tube when the normal operating pressure is 120 kilonewtons per square meter or kilopascals, and the Pitot pressure is 125 kilonewtons per square meter. Sorry, that's not exactly right. That's not yeah, that is right. Okay. So again, we use the same formula as we did before, and we multiply it out. We come to 111.8 meters per second. But they actually haven't given us the density. We're just taking this as 0.8. We actually don't know. You could assume 1 per water, where you get a different answer. The important thing here is to stay what value of rho you're actually using. If they haven't told you anything conclusive, then you just solve and express the final answer as a ratio of C over root P. Now let's move on to Venturi meters. So we've already discussed the Bernoulli theorem for an ideal fluid and laminar throw. A Venturi meter is basically a smooth contraction followed by a smooth expansion. So you've got this constricted bottleneck in a pipe, and you'll usually measure just before the fluid hits the bottleneck and at the bottleneck, and you'll get a difference in fluid heights that we're going to call H. We're pretty much working with the same values as we did before: A1, V1, P1, A2, V2, P2, and rho. And this picture is taken from Wikipedia. So we don't have a vertical component again, so we're sitting with that equation we came out with in the first time when we were looking at the previous section. And we also have Q1 equals Q2, and we say that if we solve this and look at V2, we want to find out what V2 is, which is the velocity in the neck. We get it as a ratio of A1, or area of pipe, the larger pipe divided by the bottom pipe, times the velocity in the larger pipe. And we do some substitution here, and you'll get that P1 minus P2 equals half rho. You replace that V2 expression with that whole thing squared minus V1 squared. And we know that P1 minus P2 is rho GH, which is basically, we've got the rho, we know G is 9.81 meters per second squared, and there's the H we've got. And so if we put that rho GH equals to that, to the right hand side of the equation, we can cancel out the rho's, and we solve for V1. V1 squared is 2GH over that ratio of area squared minus 1. And if we want to look at this as a flow rate, we'd say it's A1, because V1 that we're looking at, times V1, and V1 is the root of that. So let's look at another IFE example from 2016. This comes from the study guide. It says, calculate the flow rate in liters per minute in a 90 millimeter pipeline given the following information. A Venturi meter with a throat diameter of 50 millimeters, so that's D2 we're talking about, the smaller one, is fitted into a pipeline and indicates heads of 900 millimeters at entrance and 200 millimeters at the throat. So what they're saying there, go back to this drawing, it's 900 millimeters you're seeing there, 200 millimeters you're seeing there. There's the neck, there's the entrance. Going back to the example, we use this formula, Q equals A1 times that mess, unfortunately. We know that A1 is the area of the larger pipe, 90 millimeter they said here, and if we multiply that out, and the same for A2 smaller, we get these areas. We know that H is the difference between 900 and 200 millimeters. You plug in all these values and you get to 7.65 liters per second, and if you multiply that by 60, you'll get 458 liters per minute, which is the flow rate thereafter. So in the previous example, we were assuming ideal circumstances with no loss due to friction or discharge. So if you purchase one of these meters from an OEM, there will be a built-in C value something, and nothing is ideal, and you're going to lose a bit of energy and flow because of the natural, or the inbuilt friction, which is very difficult to avoid in real life situations. OEMs will try and keep it very low, but here we're going to use a C of 0.97, which means it's 97% efficient, and we're getting a 3% loss through the meter. It's actually pretty high for this kind of application, but we'll just use it as an example to see how it affects. So if we say C, if we add that constant in before, or multiply exactly by before, we get 444 liters per minute, which actually means you are losing 14 liters per minute just because of that 3% drop in efficiency. And that's pretty much it. So thanks for watching.